After watching this video, make sure you go through the experiment videos because that tells you in much better detail how to perfectly do a titration experiment, and it has all the calculations and uncertainties, etc. in there as well. And also I tell you why titrations are not good enough. You should be using a data logger, so use a drop counter to do your titrations, and there's a stack of calculations in there as well. Far superior is to go to the experimental videos. Just a little bit more detail though I can give in this video with the time given. Always do your measurements with analytical glassware, so that's volumetric glass burettes, graduated pipettes, volumetric pipettes, and micro-teeter pipettes, but they won't let you have those because they cost thousands of dollars. All these other things are for just crude collecting beakers. Even measuring cylinders don't use. Use analytical glassware because it has a very accurate and low uncertainty to it. So first of all, this is just a general way. You can always break the rules and do things slightly differently, but you can see from the experimental video how to do it properly. But we wash out every single particle, make sure it's dissolved first before you add it up. That one's sort of got too much liquid in it, and then add it up to the meniscus. The second thing you do just generally, there may be other steps to get to this. So the titration calculations I'm giving in this video are very simple, but there are much better, more complicated, more realistic worksheets on the website for you to practice. And so that's a volumetric pipette there, not graduated. And so you take a specific amount and let it drain in 45 degrees for a couple of seconds. That's calibrated to contain that drop, and so you know exactly how much liquid is in the unknown. Now when you do the titration, there should be a funnel here, by the way, and it needs to be below eye height. You rinse with the stuff that you're actually going to put in there. Just as one extra thing, because there's liquid that can stick slightly to the edges or the sides, you're allowed to wash all that down because that doesn't change the number of moles reacting. Okay, and it doesn't change your overall concentration calculations either because you're going to be using the correct additional volume as well. So that's the only one where adding extra water doesn't have any effect. It actually makes it more accurate. Now these terms here, I don't like the fact there's so many terms. You can read those for yourself. Just as a trick, if you just delete these words out in questions, and it should still make 100% sense, but read through them. You remember them, good for you. If you don't worry about it. This is important though. The endpoint, the high levels are going to go through the calculations to show why you choose a particular indicator at a particular pH, and within 1 or 2 units, that's when you can see a color change. And so that's what the endpoint is when you detect color change, and it's kind of a little bit subjective. The equivalence point is the actual correct stoichiometric ratio, and you're kind of hoping that the two are the same, and that's a good reason why using a drop counter is far superior to you doing a titration, because you'll actually get this literal curve here. You won't just be going from one color 1 to color 2 and just saying, oh, there it is, right? You can actually mathematically take derivatives and work out exactly where the point of greatest change is, and you can perfectly get the endpoint, the equivalence point, stoichiometric point, without actually technically having an endpoint. No color change. Buffer region, if it has to be a weak acid or a weak base for that, so that's for the high levels. So we could ignore that for the time being. This one here, always have a check. You should be, as you can see from the experimental videos, and I wasn't cheating, I got the exact same result again and again and again to the exactly. All right, this one's not exact. It's got a difference by the allowed uncertainty, and you're allowed to be that far wrong. That's how accurate the titrations are expected to be. If you see something that's out, probably these are going to be quite out too, because your technique, all right, you didn't use perfect technique, which you don't have time for sometimes, to be honest. I tell students just to rush through it and don't do rinsing techniques and stuff, because time is limited. Always remember to get rid of the rough, especially when it's obvious that it's a rough and it doesn't match up with the rest of them. So you start with your average. You've taken a reading before and after, so always double that. And then your final reading will be the same number of unit places as your uncertainty. So that's the number that you're working with as far as the volume of the unknown. The volume of the known. So that you know the number of moles now. So now you know the number of moles of the unknown, and you know the volume. So therefore you know the concentration. So just as a quick overview, because I'm only doing a simple calculation, just the absolute basics. So you have a known concentration with a known volume. Therefore, you know the ratios of the unknown, so you know the ratio of the known. You know the volume of the unknown, so now you can work out the concentration of the unknown. Okay, so just a basic one here. So 12 mils of a known concentration, known volume, unknown concentration. So check your ratios, all ones. Labeled formula substitute units. So that's how many moles are used. Therefore, I must have used the same. So as I said, for 1:1, you can just jump straight to that. But that's how you do the ratios, cross multiply, you get that. So now I know exactly how many moles there must have been, and I know the volume. So labeled formula substitute units, that's the concentration of the unknown. So once again, just go back and watch those 3 experimental videos. They are very, very important.